Hey, what's going on, fellow physicists? This is Hutch, and this is the Science Hutch, and welcome to both of them. And we are talking about circuits today, our very special science, and we're going to jump right into it. So, this is going to lead you through learning a little bit about series and parallel circuits. First thing you want to do is you're going to pause the video. This is going to be interactive. Hopefully, you're on your computer, obviously, watching a video here. Or an internet-capable device, you're going to go Google search physicsclassroom.com circuit builder, and the first link will take you to this site right here where you're going to, oh, no, this is the concept builder. You're going to go to the circuit builder. It's an interactive, and here's their interactives on the left, all the way to electric circuits, and here we have a DC circuit builder that I have created a circuit here. All right, you're going to go there. You're going to make this circuit here. Battery on the left, wire, light bulb, ammeter, wire, light bulb, ammeter, wire, light bulb, ammeter, wire. Pause the video now and see if you can go create this for yourself.
Talon Culver, please report to athletics. Talon Culver, please report to athletics.
See, right now I'm walking you through how to get there, and then I'm gonna full screen this bad boy, wham, and I'm gonna start hitting. So click there, you can click here, and you get these different tools. Now just click once, bring it up here, and click on the space you want to place it. Wire, let's do a light bulb, okay, ammeter. All right, now let's bring it around. We got to make a loop, so let's drop the wire down, let's put a light bulb in, boom. And then let's put an ammeter in there just to read the current again. All right, cool. Now let's bring a wire around. We want one more light bulb. We want 3 light bulbs. Light bulb, there's the last one. Boom. Let's read the current here just before it goes back into the battery with that ammeter, and boom. Hey, there we have current flowing. We get 0.3 amperes of current flowing. The light bulbs are lit. They're all lit the same amount, so they're all the same brightness. What we say is that means they're dissipating the same amount of power. They are giving off the same amount of light and heat energy every second, and energy per second is what we call power in physics. These 9s are indicating the voltage at this location in the wire. This must be a 9-volt battery. And notice that it drops from 9 to 6 after this light bulb. That's because this light bulb is going to take some energy per coulomb of charge that flows through it, and it's going to bleed it out of the circuit in the form of radiant energy, that's light, and heat. So we're down to 6 volts, which is 6 joules of energy per coulomb of charge that's flowing here. And these little pluses are indicating coulombs of charge that are flowing. Maybe not a whole coulomb, they're just indicating the charge flowing, which we call the electric current. So we're in this electric current of measured in coulombs, we are looking at 0.3 amperes of current flowing, and it is at 6 volts. That's 6 joules of energy per coulomb that flows. After flowing through this light bulb, we bleed out some more of those joules, turn it from electrical into radiant and heat, thermal, and we're down to 3. And then we go around here and we drop the last 3 over there. We call this a voltage drop, and now we're down to 0. There is a rule called the Kirchhoff's loop rule. Circuit is a fancy word for loop, that says every time you make a loop in a circuit, you have to drop all of the energy available. So the voltage has to go from the total voltage capable from the battery down to 0. And it is an extension of the law of conservation of energy. That's the Kirchhoff's loop rule. We're going to drop all of the voltage around the loop. Okay, well that was fun. Well, let's go back to see where we are. So now we've made this circuit. Now we got to learn how to draw it. We got to draw it in our journals. This is how that circuit would look drawn in our journals. A in a circle is ammeter, and then squiggly line is a resistor. A resistor is anything that offers resistance and uses energy in your circuit. We can label them R1, R subscript 2, R subscript 3, because we had 1, 2, 3 of them. I also had 3 ammeters plugged in there, and you have to let the current flow right through the ammeter, so you literally just put it right in there. All these lines are wires, and then that is a battery. This long line Parallel with a short line is a battery. The long line is the positive side of the battery, represents higher voltage. Longer line, lower voltage or 0 voltage, is the negative side of the battery. And then 9 volts to label the total voltage of the battery. Okay, pause it, get that drawn in your journals. And we're back now. Here's all the symbols. We used all of these except for the voltmeter and the switch in that last circuit. So make note about these symbols or label them in your drawing so you know what they mean. One extra new piece of information besides the voltmeter and the switch, a little door there, opens and closes to open and close the circuit to turn it on and off. That the resistance of a wire, as far as we're concerned, is equal to 0 ohms. It's an omega, the symbol for the resistance unit. Okay, so wire. We're using basically magic wire, imagining that the resistance is negligible, so it's so small we can neglect it and call it 0. Let's move on. Now, when you're looking at your worksheet, let's see, it's fine. Here's the worksheet, okay? You find this worksheet. This is a circuit builder worksheet that goes with the activity we're doing right now, okay? And so when you've got this worksheet, this part right here gets filled in like this according to our picture right there. We read the 3.3 amps off of the ammeters and boom, filled it in right there. And then all the voltages were at 9 along here, dropped to 6 in this orange area, dropped to 3 in the green area, dropped to 0 in the blue area. We are color coding the circuit here to show warm colors indicate high voltage, and then they cool off as the energy cools off to 0, where blue is going to be 0 volts. All right, let's see about parallel circuits. That was a series circuit. Let's see about parallel. So we're going to make this circuit. Go ahead and pause the video and see if you can go create this circuit in the circuit builder. Pause. Go. Pause. Pause it. Pause it. Okay, if you didn't pause, bad. But over here, this is mine. Whoa. Look at how the current is flowing. Much faster here, slower in these branches, and that's because the current, there's more current here. How much current? 2.7 amperes of current. And then it splits. 0.9 goes down this loop and back around, and then 1.8 goes this way. Now, if you add 0.9 and 1.8, you will get 2.7. So the current is splitting and taking multiple paths. So when we have parallel circuits, we have plural paths. You can use those alliteration, parallel plural paths, all the P's. And then it splits again to 0.9 this way, the outer loop, and 0.9 down here in the middle. So we have 3 different loops here, and we have the current has to split to take one of those 3 different loops. So all of it together here, 2.7. Some of it splits, 0.9 goes this way. Some of it splits, 1.8 goes here, 0.9 down this track, and back to 1.8, back to 2.7, and back to the battery, and then split again. So we have 1, 2, 3 loops. Now, according to Kirchhoff's loop rule that we just talked about, you have the 9 volts of the battery. Here they are, all the energy in that current that is flowing, and then the current that goes this way has all that energy still. It hasn't lost any of it. And then we hit this light bulb. Super bright. Look at that super bright light bulb there. That's because it is dropping all 9 volts so that it's 0 here, 0 joules per coulomb of energy left, all the way back to the battery. So if you take this loop, there's 3 different loops here. And according to Kirchhoff's loop rule, for each loop, you've got to drop all 9 volts. So you're going to drop all 9 volts here and come back to the battery. But the current that didn't go that path, the current that took the middle path, it still has 9 volts. It didn't lose any energy because it never went down that light bulb. So it's going to go, oh, it's going to hit in the middle. Oh, it's going to drop all 9. There it goes. Oh, now it's 0 all the way back to the battery. Oh, what about this current? It's going to take the outside track. It hasn't lost any energy. It didn't go through any light bulbs across the top. And then it still hasn't lost energy. And then it hits this light bulb. Boom! Super bright light bulb because it's dropping all 9 volts. So you're going to run your battery down a lot faster here because you are using up a lot more energy, and that's represented by these light bulbs being a lot brighter in parallel. Another thing about these light bulbs is if you take one out in parallel, the other 2 stay lit because these are independent pathways for the electricity. So they don't need each other. And notice what happens to the current. The current actually lowers because you have more resistance when you have less pathways to run. So when we add more pathways, you're actually offering more roads for that electric traffic to drive on, and that cuts down the overall traffic congestion. That cuts down the resistance total for the circuit. Okay, let's go back to here. Let's draw this in our journals. So pause the video, draw this in your journal here. We've got ammeters all over the place because we wanted to measure all that current that was splitting in amperes. We've got our 3 resistors here that were light bulbs, and they were wired in parallel branches. Pause it. Pause. Pause. Pause and draw. Okay, now we're back. We are back, and now this is how this will look in your worksheet. Whoom, to the second page of the worksheet. We're down here now. When you are coloring this, okay, you want to color like the 9 volts was red, or it's the highest voltage there. So it's all red all along here. And then you have that big drop down to blue at each light bulb. So that's why each light bulb is so bright, because each light bulb gets the full 9 volts of the battery. And that's why the battery will run down faster. So that's the only disadvantage to wiring in parallel. All right, and then we're labeling all of our currents here. Boom, 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 boom. We got all the currents labeled there. So boom, awesome. Okay, now let's move on to getting some rules for resistors in series. Little alliteration here for you. Series is single path. So if you have a single pathway, you're wired in series. In series, your voltage drops are going to add up to the total. Your resistances are going to add up to the total. So if you have the resistance of, let's go to series, each of these light bulbs, 1, 2, 3, then you're going to add those resistances together, and that'll be the resistance of the total circuit. You're also going to add up the voltage drops here. We saw in that series circuit, where did we see that? Okay, we went from 9 to 6. So that voltage drop was 3, and then 6 to 3, that voltage drop is 3 again, and 3 to 0, that voltage drop is 3. 3, we're dropping 3, we're dropping 3, we're dropping 3. 3 plus 3 plus 3 is going to be 9, which was the total voltage of the battery. And that's what we're talking about with those voltage drops adding together.
Please dial 1104. Ms. Zipkowski, please dial 1104.
All right, hopefully Ms. Zipkowski dials 1104. All right, so the voltage drops add to the total. We saw that 3 plus 3 plus 3 to the 9 volts of the battery. The resistances we did not calculate because we don't know the resistance of the light bulbs yet, but they would add up. If you want to know the total resistance of the circuit, you just add all the resistances of the light bulbs. And then the current is flowing. The same current was flowing everywhere. If you look back at your circuit, you'll see 0.3 amperes of current flowing everywhere you measured it with an amp meter. Here's a memory device for you. This is called an acronym.
Talon Covert, please report to the athletics office. Talon Covert, please report to the athletics office.
Okay, hopefully Talon Covert reports to the athletics office. Some adults view resistances so carelessly, and the SAVRSC are connecting to this statement underneath. This statement puts all of these rules together into one statement. So in series, S for series, A, add voltage drops, V for voltage drops, your resistances add, S for same, carelessly for current. So series, you're going to add your voltage drops and your resistances to get the totals. That's these 2 facts up here. But you're going to see the same current flowing everywhere because there's only a single path for the current. It never needs to split. Now, what about parallel? Well, in parallel, you're going to see plural paths. So we call these paths branches. And we saw 3 different branches here. We saw 3 different paths. So plural pathways, many pathways. And we're going to see the same voltage drop across each branch. So we saw here 9 to 0, 9 to 0, 9 to 0. We saw a 9-volt drop across each of those. So same voltage drop. The resistances, we do this mathematical magic that I'll have to show you later, where you inversely add your resistances. And what that does is it mathematically gives you a sum that is less than any of the resistances you added together to make that sum. And we'll learn that later. And then the current. So what's important to know now is that if you add more branches because you inversely add your resistance, the overall resistance of the circuit actually gets less. That's like adding more like traffic roads into and out of a parking lot. It's going to be easier to get traffic in and out of that parking lot if you have more roads in and out. So that's more paths. So even if a crappy road is put there and only trucks and SUVs can make it over a dirt muddy path in and out of that parking lot, that's a lot of resistance driving that road. But overall, the resistance to moving in and out of the parking lot is less. So that's what happens when you add parallel plural paths to your circuit. You get less resistance overall. Okay, now what happens to the current? Well, the current splits. The current has to split, and some goes along this loop on the inside and comes back. Some goes on the outside loop, some in middle loop, and so the current gets added up. You add the current that takes the inside, the middle, and the outside tracks, and they add up. So we see like 2.7 was the total current. 2.7 amps. Then 0.9 takes the middle, 0.9 takes the middle, 0.9 takes the inner, 0.9 takes the outer. You add all those together, you're going to get 2.7. Where these 0.9s are coming back together, right here in this middle part, you're getting 0.9 amps flowing back together with this 0.9 that flows back together, you get the 1.8. And once the 1.8 flows together with this 0.9 that took the inner path, you get your 2.7 again. So there's how the currents are going to add together to the total in parallel. So here's my memory device for parallel. PS, voltages are currently in a revolt. And that goes together with P for parallel, S for same, voltages or voltage drops, R for add, currently is currents, and NA is inversely add, revolt resistances. Okay, hopefully that's helpful. Now what you're going to do to practice this out, you're going to go to this concept builder, Know Your Potential, on the physics classroom, and you are going to engage that Know Your Potential. There are 3 levels: color those wires, which bulbs will light, and volt on it. And you're going to put your name in there first and last, and you're going to get these trophies. You want to take a screenshot of this with your name in there and send that to me, and then you have your grade for your homework. All right, happy physicsing, and thanks for watching. Good luck, everybody. Bye-bye.